Hello everyone and welcome back. Today we will be doing yet another systems design problem, probably going to be Amazon retail. Now if it looks like I'm going to pass out, that's because I probably am, so I'm going to try and keep this video relatively short. However, if you guys are anything like the women that I've seen in the past, apparently the long ones are too painful anyways, so hopefully this should be just good for you. Let's go ahead and get started. Alrighty, so today we're going to be building Amazon, or for you lovely folks over in India right now, Flipkart. Basically, the idea of this is, as we know, you can go ahead and see a product. Once you see the product, it has some price, probably an indication of whether or not it's in stock, a button to add it to your cart, and then of course, once you're on the cart screen, you can go ahead and place an order. So as you can see in my cart, it shows the items that I've currently got ready to check out. I've got some lotion, some socks, some motor oil, a broom. No relation between any of those items, just random stuff that I picked out. Cool. Let's talk about some problem requirements. So the main things to do here are we obviously just want to build some pretty limited feature set of Amazon's retail site, which at least as far as I'm concerned, what's hard to build or what's worth building for the sake of this video is going to be the cart service, basically dealing with inventory management, dealing with when items go out of stock, and just in general making everything fast and scalable. A couple of features that we aren't going to cover as far as Amazon is concerned are the reviews. We basically did that with Yelp. It's the same idea. Payments probably deserves its own video, if anything. Anything related to Amazon Web Services, you're on crack if you think I'm covering this in this video. Or, of course, any user or seller customer service related type of things. I have a friend who works at Amazon on one of these teams, and it just goes to show you it deserves an entire team, right? So obviously there are tons of complicated services going on Amazon retail. However, nonetheless, we're just going to cover a very small piece of that. Cool, so let's talk about some quick capacity estimates. These are going to be super hand wavy because it just changes constantly and you're kind of at your whim of your interviewer here when you're doing this. So first off, let's assume there are around 350 million unique products on Amazon. I Googled that one, so why not just round it up to a billion? We want to build for scale. Additionally, apparently there are 10 million orders per day. Now we see why Bezos is so rich. That, if you divide by your 24 hours, your 60 minutes per hour, and your 60 seconds per minute, leads us to around 100 orders per second, which is actually not so bad if you think about it, just considering the fact that most of those orders are probably going to different databases or different product IDs, and those will probably be spread out over different databases, but we'll talk about that later. The next thing is that I basically start getting really hand-wavy here and say, let's estimate we have around a megabyte of data per product. If we multiply our billion products by our megabyte of data, that's around a petabyte of total data. So we're obviously going to be needing some partitioning over our products database, which is not a huge deal. Keep in mind, all these products have images, so at some point we want to throw them in S3, maybe use a CDN to speed up those load times. And then finally, regardless of how much scale that I listed out here, if you were just like, I'm going to throw this on one database, your interviewer is probably going to be like, you need more scale than that. So we're just going to try and imagine that everything is as slow as possible and that we've got 10 bajillion users editing everything at a time, and we're just going to try and build something super bulletproof. Cool. So what is the high-level overview? I got a comment recently kind of saying that I should try and structure my videos a little bit better, so I'm going to attempt to do that with this very slide. Apparently, and I've heard this in reference to Amazon and other e-commerce sites, even so much as 100 milliseconds of a delay on our load times can really hurt our conversion rates in our site. And so as a result, we want to make reads as fast as possible wherever we can, especially when loading potential products, actually clicking into a product to see the view of it, and then checking out as well, because we want to make writes fast as well. Cool. So if I had to make a table of contents here, for the one thing I'm going to cover really quickly is our products database, then our cart service, then dealing with placing orders, and then finally just optimizing reads in general. Cool. So the first thing that we're going to talk about is our products database. So like I mentioned, we basically have a petabyte of products data to store, or we can imagine that we do. And if that's the case, we're going to have to go ahead and partition this thing. Additionally, we also want to be ensuring fault tolerance, and if we do that, even within all of that, we want to make sure that reads are as fast as possible. So generally speaking, I don't really think we have to worry too much about write throughput here, because editing a product database description is probably going to be something that like an administrator or a seller might do, and they're probably not doing that too frequently. I would imagine it's very infrequent that two people are going to be editing the description of a product at the same time, and so as a result, I mainly care about our read throughput here, as opposed to our write throughput. So I think single leader replication should be fine. I think that using a B tree in theory is going to be optimal because, as we know, B trees are just, go down the tree, and find your read, as opposed to an SS table where you have to actually check multiple of these SS table files, and that is obviously going to take longer. Of course, the B tree is going to be slower to write to, but we don't really care if we don't have that many writes to it. Cool. So another thing is, as far as Amazon products are concerned, I think that we want to be able to have a flexible schema here. The reason being that products are in many different types of departments, and they have many different pieces of data amongst them, and so having that flexibility could be useful. So this is one of the very few cases where I'm interested in NoSQL solely for the data model, or the flexibility there, and I think that MongoDB is going to be the choice here, considering it is a single leader replicated B tree index type of database, and also allows us to just make JSON documents for products. I think we are typically going to want to load that full JSON document at once, so the data locality is actually going to help us out here. And we don't really need to do very much denormalization. We're literally just loading the product. It's not like there's any joins that we need to do, at least not in this very stripped down version of Amazon. Cool. The next thing we can talk about is actually building a cart. So I'm going to discuss a few different implementations of how we can do this, ideally getting better and better as we go. So I guess the same, the kind of idea here is we don't just want it to be the case that one person can edit their cart at a time. I might have my account open, you might have my account open, we could both be editing that cart at once. And if we're doing that, we don't want to both be stepping on each other's toes or just having super slow writes. Cool. So what would be a really bad implementation? Well, I guess it would be taking the full list that you have in your JavaScript front-end application and just sending that over to the database and overwriting the existing cart with it. Why? Well, for starters, if two people write at the same time and one isn't aware if the other's right, one is just going to override the other. So if we already had eggs and ham over here, oops, did the wrong thing. If we already had eggs and ham in the database, and then this guy writes milk and carrots, that's just going to completely get rid of it. That would be bad. We don't want to step on each other's toes like that. Of course, we could also just store the cart as a list and then basically add elements to the end of that list. Right, so I'm going to add ham, this guy's going to add eggs, but that's not going to be great either because we're going to have contention. When we're adding elements to the end of a list, we need to grab a lock on the list itself in order to add that element. And so as a result, if we have tons of people, not just two guys, but maybe 10 or 20 trying to add to the end of the cart, we're going to have a lot of contention on this lock. Now, of course, in reality, is it going to be the case that we're going to have 10 people editing the same Amazon cart at the same time? Probably not. But like I mentioned, the whole point here is to basically push this problem to the extreme in order to ultimately think through some fundamentals of systems design. Cool. So let's continue talking about building a cart. Ideally, we don't just want to keep a list because, like I mentioned, whenever we have to maintain order for something, we're going to have to grab locks in order to append onto the end of that list. So what could we do instead? Well, in order to avoid having to lock, we could just do a set. Right, so as opposed to adding things in a list, basically what we could do instead is add things to just a typical table where you've got your cart ID and your product ID. And since these two aren't actually contrasting with one another, we can just throw them into the table and you don't have to basically have the two compete with locks. Cool. However, the one situation where we would have to grab locks is if we want to be able to delete items from our cart. Right, so the person who adds this item right here and the person who deletes it, one is going to have to grab a lock on that row to add it, and the other is going to have to grab a lock on that row to delete it. Otherwise, we would have race conditions, and you have no clue what's actually going to happen. So, of course, like I mentioned, again, this is all going to be super hypothetical. Are we ever going to really have a lot of adds and removes of the same item within a second? Probably not. Maybe I'm desperately trying to add 20 boxes of tissues to my Amazon cart, and my mom keeps deleting them because she's pissed at me buying too many tissues. However, I don't really think that's going to happen in real life, but again, we're going to pretend like it does. Cool, so let's imagine there was a ton of contention on a single one of these rows. How could we avoid that lock in contention? Well, generally speaking, at least as far as I've come across, or what comes to my mind when I was making this video, I can think of kind of two main ways to try and deal with avoiding contention, right? So the idea is if we're going to have to grab locks to write two things that compete with each other, Ideally, we have two options. One is basically we process them one at a time by first buffering them in a centralized place like Kafka. In this case, I don't really think Kafka is going to work very well. The reason being that if I add an item to my cart, then it's going to go in Kafka and be processed asynchronously in the background. So if I add an item to my cart and then I click checkout, unless Kafka has already allowed that message to be processed, now all of a sudden I'm going to check out a bunch of items and I might not even have the one that I just added. So that would be bad. We definitely want something that's going to be at least synchronous here, or synchronous so far as when I add an item and then I check out, I can see that I actually added that item and it's part of my cart. Cool. So our second option would to actually just be to send all of the writes to different places so they don't have to compete with one another. And in this case, when we say different places, what that really means is multiple database leaders for that particular cart. So a couple of things or complications are going to come up here. If we have multiple leaders, how is it that everyone is going to end up seeing the same cart? Well, they won't. There's going to be eventual consistency, but we can actually ensure eventual consistency by virtue of using a CRDT. So these are something I talk about relatively frequently on this channel. A CRDT stands for conflict-free replicated data type. And in this case, we want to use such a CRDT to build a set amongst our leaders. So the idea is we're going to have a CRDT on every single one of these leaders. Each of them is going to basically have its own copy of what it thinks is in the cart, and then eventually those guys will sync up with one another, and then they should all converge to the same value. So what I'm going to demonstrate in the next slide is something called an observe remove set, which is going to allow us to build out a CRDT set where you can add, delete elements, and then add them back, which is not trivial. And the one thing to note here is that, like I mentioned, there are multiple leaders. And so if we do have multiple leaders, in order to avoid the case where I write an item to a database, then check out, and my item is not in the cart, we should make sure that if I'm writing to a database or writing to a leader of a database, one of the many, that I should also read from that same one so that I can actually see my own items on the checkout. Otherwise, you basically make it possible such that you check out and don't have the item in there that you just added. Cool. So hopefully that all makes sense so far. Let's go ahead and talk about this observe and remove set. So basically the overarching idea here for this CRDT is that one, it's an operation-based CRDT. So I'm not going to be throwing my whole set in the database every single time. I'm just going to be throwing in the element that I added or removed. And the main idea is that every single element that I add or remove, we're also going to append some unique tag, which is really just going to be a random UUID. And basically what we're going to do is we're going to throw that unique tag on the product ID whenever we're adding or removing an item from the cart. And that's basically going to tell me what a given client actually knows was in his version of the CRDT when performing an addition or a removal. So let's go ahead and demonstrate this. Let's say that at timestamp 1, we've got one client making a write to this left database over here, and he wants to add product 12 to the cart. So we assign this random tag AZ32. Is that a delete? No, it is not. At timestamp 2, this guy over here is going to read from this leader and sees that product 12 is in there with that given tag AZ32. So now his client is going to say, hey, I want to go ahead and delete this thing. How do we delete a given item? Well, all we have to do is put it in the database with the tag 12 AZ32 and a given delete, saying, okay, we actually got rid of this thing. Cool. The next aspect of this is going to be at timestamp 4, we have yet another client who says, oh, you know what, I'm also editing this cart, I want product 12 too. Since this is a unique addition, we're actually going to generate yet another new tag, in this case 6027, and that of course is not going to be a delete. So the main idea here is that when we eventually merge together all these operations, both databases are going to agree on what the general state is. So now, because of the fact that AZ32 was actually deleted and added, we know that we can basically just cancel this guy out from both of these replicas once they sync up. So AZ32 is going to get deleted, but note how this user never actually deleted product 12 with tag 6027. So this guy sticks around, and this is actually going to be the eventual result of our CRDT. We basically would agree that 6027 was still in the set and not yet deleted. However, in an alternate set of events, what would actually happen is, let's say, this guy is actually going to go forth And what happens at timestamp 3 is this guy adds 6027. However, at timestamp 4, this guy both deletes AZ32 and he deletes 6027 because he sees them both. He's actually read from this database first, and then at timestamp 4 goes and deletes them both. Well, in that case, we would have nothing remaining in our cart. He actually just deleted product 12 entirely. So hopefully that makes enough sense for how you can both delete products and also add them back. The tag is basically going to be the source of truth. Cool. The next thing that we're going to be talking about here is going to be our order service. So the general overarching theme here is whenever we create an order, I have to check whether there's going to be stock on that order. So how do we check if there's stock? Well, obviously for each product, there's some sort of counter saying, here's how much inventory I have left. You know, product 10 has 100 left in stock. So if I'm going to buy 5 units of 100, or product 10, now I have to decrement that quantity from 100 to 95. And if you recall, every single time that we have to do some sort of decrement operation or something like that on a counter, we have to grab a lock on it. Otherwise, we can have lost updates. So for example, if I have this counter here 10 and 2 different processes both try to add 1 at a time, what that really means is they first have to read the current value, add 1 to that, and then write it back. So as you can see, if they both do that at the same time without locking, they can basically both read that the current value is 10 and both write back 11. That would be a bad race condition, hence the need for the lock. So if we do have to grab a lock, that of course opens us up to lock contention. So like I said, in reality, this probably isn't such a big deal, right? We mentioned we have around 100 orders per second. Since all of those orders are on different product IDs, we're going to be grabbing different locks for each of those 100 orders. I imagine there's not really that much contention in reality. However, of course, for the sake of this problem, we're going to pretend like there's a ton of contention. So what are we going to do in such a scenario? Well, let's go back to our avoiding contention playbook. Basically, there are 2 things we can do. One was what we did last time, where we have multiple leaders and we attempt to basically use some sort of eventual consistency in order to distribute out our rights to multiple different places so that we don't have to grab as many we don't basically grab the same locks on each database node. Cool. So in this case, let's imagine we use something like a counter CRDT. So this is something I've covered in the past, but basically the idea here is that you keep track of the number that you have basically incremented on every single leader instance, and then eventually those guys will sync together, and then you'll have a good idea of the total number of increments, or decrements in this case. But the idea here is basically we could effectively see the remaining quantity of orders, or at least as well as each leader database knew it to be, and those guys would eventually converge. However, the problem is we only actually find out the true value of the CRDT once these guys actually sync up with one another. So let's imagine, I'm just going over to this example right here, and I'll erase what I had so that I can write it out again. Let's imagine that we both start out with 10 remaining quantity on both of these guys. Now the first thing that's going to happen is, let's say one order comes in, it goes to this database over here, and it was for a size of 10. And then this guy comes over here, going to the right database, and it was also for a size of 10. Now these guys sync up and they say, oh shoot, what actually happened is that we oversold our product by 10 units. We accidentally sold 20 and we only meant to send 10. Now we have to go back and tell everyone that even though we told them that they had filled their order, they didn't actually. So what would be a better solution than that? Well, ideally, we have to use our other possibility, which is going to be some sort of buffering our events, which we do in Kafka, and then processing them one at a time via a stream processing framework. So basically, the idea now is that the orders are going to go into a Kafka queue. We can partition these by product ID if we need to actually scale them out because there are so many product IDs. And then basically, once we figure out whether we actually have the proper amount of stock for a given order, we can go ahead and email a user. Now keep in mind that the emailing users part is not idempotent, right? So if for some reason our Flink node goes down, or whatever it is that we're using for stream processing, after we send that email and we don't actually acknowledge the fact that we sent the email, we're going to rerun this event from Kafka, send another email, and tough luck, our client gets 2 emails, but not the end of the world. Just note that it is not idempotent unless we use two-phase commit. Cool, or It wouldn't be idempotent if we use two-phase commit, but if we did use two-phase commit, it wouldn't be possible for us to end up replaying that email because we would acknowledge the message at the same exact time that we sent the email. Cool. So now I have myself a little diagram here to explain how order processing is going to work when we are using streaming. So we've got our order service over here. This is where I come and place myself an order, for some tissues and some lotion. Now the first thing that's going to happen are these guys are two different product IDs, right? Tissues could be product ID 22, lotion could be product ID 50. So over here, the first thing that's going to happen is that exact message is going to be sent into this very Kafka queue. And the nice thing about using one Kafka queue for the whole order is that that is going to assure atomicity. We know that once this message is in Kafka, it's eventually going to be processed by the rest of our components, but before it gets there, if I wanted to split these guys up and try and send them both into the same Kafka queue, well, it's possible that one gets there and the other doesn't, and then now we only process half of our order. So again, it's very nice to basically have a unified Kafka queue for our orders, and then once it actually gets in there, we can use Flink to basically guarantee that every single message is going to be processed. So what our first Flink node is going to do is actually split up these orders. So I'm going to call this the order splitter Flink, whatever, bad name, who cares. It's basically just going to route each individual component of the order, so each product of the order and the quantity that we actually want, into the proper Kafka queue for it. So these Kafka queues are sharded by product IDs. So these would be the individual product orders. Cool. The last thing that's going to happen there is we're basically going to take a product ID, we're going to take the quantity of it that we actually want to buy, and then we are going to check its current quantity on the Flink node. So let's imagine I wanted a 3 quantity and there were 3 remaining. What I would do is basically decrement this 3 to 0. I would send an email to the client saying you're good to go, we actually filled this order. And then the next thing that I would do is say, oh shoot, this thing is at a 0 quantity. Let's go ahead and write that this product is out of stock to our product database. The last piece of the puzzle is, well, how is Flink actually able to cache basically the current stock of a given product? Well, besides whatever incoming orders there are, it also needs to get any incoming inventory changes that come from our sellers. So what our seller can do is, if this is our seller, he's basically just going to upload, hey, for product 10, we just added 250 more stock. And then this guy would flow through Kafka back into our Flink consumer, and then this 0 gets edited to 250 so that we can start fulfilling subsequent orders. Cool. Hopefully that all makes sense right there. The last aspect of this video is going to be attempting to optimize our reads. So like I mentioned, basically, the faster that we can make the reads on our service, the more likely that we are to sell products, and that is a huge deal. So the idea is, we can't make all of our reads fast, right? That would just be put everything in memory, get everything in a cache. That would be nice. So a certain subset of our items we want to ideally make the reads faster for. So which items would these be? Well, ideally the popular ones. Cool. So the first question that should come up is, which items are popular? Many different ways to determine this. I'm sure Amazon has a variety even internally. One would just be the number of orders on a product, another would be the number of clicks on a product, etc., etc., etc. Maybe the reviews on the product. It doesn't really matter. I guess the idea is, at the end of the day, we're doing some sort of counting aggregation over a time window. And we might want to export those metrics, let's say once per day. So of course, you already know what I'm going to say. What are we going to do? Stream processing, because then we can window our data and say, hey, here are our metrics for the last day. So let's say we use Spark Streaming because we just want to process things in mini batches. No reason to process them one at a time. It's not that urgent. So let's say we keep all of these counts in Spark Streaming. Let's imagine that we're doing this based off the number of orders on a product, right? So in Spark Streaming, right over here, not only are we keeping track of the actual quantity remaining, but we're also keeping track of the number of orders. So we're going to do that. And then once per day at some set time, we can basically export for each product ID the number of orders that they had, and we can send that right over to HDFS. Now, once this guy is in HDFS, or once all of this data is in HDFS, we can actually go ahead and run a Spark job to basically rank all of the items in terms of their popularity. We would calculate some popularity score, we would rank them, we could even split them into given departments, right? So for example, I don't know, all the silverware, all the mattresses, all the video games, rank them all in their own categories. And we could even do some exponential weighting, right? If I have yesterday's data and the days before that, I can slightly incorporate those into my popularity score, but I could weight today's data more heavily. Again, this is all implementation details. You have a lot of options here for how you want to do this ranking. Doesn't really matter. But the point that does matter is that once we know which items are particularly popular, sorry about that, we can go ahead and pre-populate our caches with them. So we can do that with basically the product data that we see in MongoDB. We can throw that in a Redis cache for products. And additionally, we can take those corresponding images of the products and throw them in a CDN. The nice thing about a CDN is, of course, that it's geographically distributed, meaning that for a given product, ideally, since those images are so big, if the CDN hosting the image is physically closer to me, I can load it faster. Cool. So another part of reads that we really want to optimize is going to be text search. So, of course, if you go to Amazon, one of the things that you're going to notice is that we have this massive search bar at the top, and you want it to be quick when you say search for a given product. So if I want to search for a mattress, I want to see only mattresses, and I want that to happen really quickly. Now, if you've been watching my channel for a decently long time, you would know that a search index is going to be completely necessary here, and what that really is under the hood is just going to be an inverted index, where an inverted index is an index from search term to a list of product IDs or product descriptions that contain that search term. Cool. And so in order to make things even faster, I said product ID over here, but what would really be better is an actual product description, or perhaps a mini one. Maybe not everything that's in Mongo, but perhaps like a thumbnail of the product, because then we don't have to actually go back to Mongo to do an additional read once we hit our search index. So a little bit of data denormalization is probably going to be in order here. Cool. So the next question is going to be, how do we actually want to partition our search index? Well, we could do global term-based partitioning, right? Which would be super nice. So if I ever search mattress, all of the document IDs or the product IDs that contain the term mattress are going to be on a single node. That would be great, because then if I ever do that search, I am basically only going to have to hit one node. At the same time, in reality, there are probably too many products, especially when you consider their description sizes, in order to be doing that. The reason I say that is because keep in mind that if we want to keep a global index, what that basically means is that the same product is going to have to be on multiple different nodes, right? So for example, if we have the term Kleenex on one node and the term tissues on another node, on node 1, I now have to keep the full product description, and on node 2, I also have to keep the full product description. So now we're really duplicating data, which is not ideal. Another thing about global-based partitioning is, do we really need all of those product IDs on the same partition? Perhaps not, because at the end of the day, on our front end, we use pagination. So as long as every single document ID on a given page of Amazon is on the same partition, we can still get super fast queries. Cool. So let's talk about local indexing, because that is really our only alternative to global indexing. The idea here is that basically we put a set of products on every single node of our search index, and then we index them locally. So we just build that inverted index locally right off of that set of products. So let's imagine that basically we have one product called Kleenex tissues. As you can see, the term for Kleenex and the term for tissues is going to be on this particular node. If on a different node we had, I don't know, softy tissues, they would also have the term tissues on that node too. Okay, cool. So that is what local partitioning is, but now the question is, well, how do we want to perform local partitioning? We have to decide now which products are actually going to go on which node to be locally partitioned. Cool. And when I say locally partitioned, typo on my end, locally indexed. Great. So what products are going to go on each partition? Basically, the main thing right here is that we want ideally similar products to be on the same partition, and also similar product categories, which would be a little bit easier, because I would imagine that in that MongoDB, most of these products are going to have some sort of tag So for an example, a tag would just be mattress, or it would be gardening, or something like that. So similar products can go on the same search index node. And additionally, in our batch job, keep in mind we basically have generated a popularity score for every single product category, right? So here's the mattress product category. We've got product ID 12, it's got a score of 3.6, 19's got a score of 2.1, and so on and so on. So ideally, keep in mind that this is effectively also going to be the order of items that we return when we search for the term mattress. And so as a result, what's going to be nice about this is that as long as we partition by popularity score range, now if I want to say search for page 1 of mattress listings, I basically just want these terms right here. If I want page 2 of mattress listings, I want these terms right here. And so we can actually just go ahead and partition those accordingly, which is going to make our life pretty easily. So to summarize that, first we partition the products by their product category, and then internally within a product category we can partition by their popularity score that we calculate in Spark. Cool. The last piece of this puzzle is actually going to be doing the population of both the caches and indexes after we go ahead and compute our popularity scores for all of the products. Well, ideally, we don't want to basically do this into our current caches and indexes, or our current cluster. The reason being that this is going to slow it down by a lot. If we add a bunch of writes to that current cluster, that is going to compete for a lot of the networking bandwidth there, and it's going to slow down actual user reads, and that would be bad. So ideally, what we could do instead is have some sort of standby cluster. Now, we don't have to have this provisioned at all times, but maybe 30 minutes before our batch job runs, you provision a bunch of EC2 instances or something like that, depending on what platform you're actually using here. And then the first thing that you're going to do is basically go ahead and populate them from Spark, right? So you're going to add stuff into your standby cluster. The next thing that you're going to do is go over to your Zookeeper or whatever coordination service it is that you're using to basically tell everything in your application where everyone lives, or your DNS service or anything like that. So we go to Zookeeper, we say, hey, wait a second, we're now using all of these URLs that points to our standby cluster. And then all of a sudden we're going to broadcast that to all of our existing servers via something like a Zookeeper watch in order to keep them updated in terms of where to actually point their queries. And then, maybe 20 minutes later, we go ahead and decommission the nodes in our current cluster because they can become a standby eventually. We don't want to waste a bunch of money. Additionally, one other point here is you could probably do this on like a region basis where you purposely choose a time to do this where that region has most of the people sleeping, so traffic is particularly low. But those are other considerations you can just talk about with your interviewer. Cool. My voice is starting to give out on me, so give me about 1 second here, and then we will talk about this. Okay, so I'm now going to try and demonstrate the flow of how Amazon is going to work. So the first thing that we can do is actually just search for products off a given search term. As we know, that means we're just going to be hitting our Elasticsearch. So like we mentioned, Elasticsearch is going to work really nicely for us here if we shard by both the product type or some sort of product tag and also some sort of popularity score range. We can evenly distribute these out pretty easily because we ran a batch job, so we know how big the whole sample size is, and we can distribute those as necessary. Cool. The next aspect of this is going to be the product service. This is once I perform my search, now all of a sudden I see a thumbnail for an item, I want to click the item and get the full product description, so this is going to be the second thing in the pipeline. So either that product is going to be in our product cache because we preloaded it there because it's a popular one, or if not, we hit our cache, get a cache miss, and then we go over to our product database, which again is going to be Mongo, so we get that flexible data format with JSON documents, and then we can just shard that on the product ID. Cool. Hopefully that makes sense. Number 3 is we submit an order. Actually, technically, we would have to put things in the cart first, so cart is going to be number 3. Here, I've basically lined up our cart DB. So keep in mind the schema is effectively the cart ID, the product ID, and whether or not it's deleted, as well as the unique tag of that product ID. So we're going to do that in Ryak. Ryak is not a database that I talk about super often on this channel, but think of it like Cassandra, but it supports CRDTs. So Ryak would work very nicely here. Cool, so we're going to just partition by cart ID there so that all of the writes for a given cart are on the same node. And as a result of that, when we do perform our anti-entropy, all of our state will eventually converge. Cool. The next aspect of this is going to be the order service. So the first thing that happens, as we discussed, in order to keep things atomic, is we send our full order into the full orders Kafka queue. From there, Flink is going to take it in, split it up into multiple different orders. This then gets sent into a second Kafka queue where we have orders per product ID, with, of course, the amount of stock in that product ID that we want to buy. And then finally, that's going to hit our last Flink node, which performs our inventory checks. So this Flink node is basically going to take in inventory changes, which is just a Kafka queue. And if you are someone who is selling things on Amazon, you can write your incoming inventory changes to that Kafka queue. For example, product 10, add 250 stock. Product 10, remove 100 stock. Flink can take those into account. The last aspect of this is that, obviously, once we go ahead and process whether an order can be processed or not, we would actually want to send an email over to our user that made the order. So we are going to have the email address associated with the order somewhere in our data model. Finally, of course, like I mentioned, we want to get some aspect of how popular a given product is. So in this Flink node right here, which is sharded by product ID, and keep in mind it's sharded by product ID because Kafka is sharded by product ID, and we have one Flink consumer per Kafka shard. Basically, what's going to go ahead and happen now is that we can aggregate the number of orders or the number of stock purchased from an item in a given day, upload that to HDFS at the end of the day, and then run our Spark batch job to, 1, update the products database, or rather actually update the product cache over here. Jordan, stop erasing. Update the product cache, update our Elasticsearch instance to basically rebalance our partitions by their popularity score. We would do this in the standby cluster, but I just didn't have enough space in the diagram. We would update Zookeeper to basically go ahead and say, hey, we're going to have to switch over to our new Elasticsearch and our new caches and our new CDNs, etc., etc. And yeah, that would be it right there. Once we switch over, the user starts reading from all of those in particular. Well, guys, I hope you enjoyed this video. Again, apologies, I'm so tired and my voice is giving out. However, I do think this one was moderately understandable compared to the Reddit video. So hopefully it worked out well, and I will see you all in the next one.